Yeah, okay. So welcome everyone. So today is our pleasure to have Xiong Wang, who will be talking about statistical learning problems in interacting particle systems. Yeah, thank you.
Okay, thank you. Thank Dr. Hansa for the invitation, and I'm very happy to be here. So my name is Xiong Wang, and I'm now an TDAP at the Sun Yat-sen University, at Guangzhou. So if you visit Guangzhou, like yeah, I think I'm more familiar with this city than ChatGPT. So if you visit here, please let me know. I can definitely introduce a very good Cantonese restaurant for you. Okay. Uh, Today I want to share our group's work on the stochastic learning problems in the particle systems. So I will, I will, so, okay, let me check. Okay, yeah. So this talk is based on the following three papers or preprints. And so today I will probably face the first two papers, especially the second one. So actually, when I was a PhD student at Canada, so I focused on another field is the stochastic partial differential equations. And then when I came to Johns Hopkins, I shifted my interest to the machine learning and also in the particle systems. So I really learned a lot from my collaborators, Chuan Junfei, Molo, Yinba, and Shuai. So here, I really need to say thank you for all of them. And okay, yes. Next, let me talk about the table, the content of today. So I'm pretty sure that everyone in here, like many experts on entire particle system, but still I want to give a very quick introduction to the entire particle system. And then I will talk about the learning problems in entire particle systems. Okay. Okay. And also, if you have any question, just let me know. Okay, I would happy to discuss. So first, let's talk about entire particle systems. Well, in this talk, so just make sure everyone on the same page. So in this talk, when we say entire particle systems or IPS, it basically means the stochastic systems considering particles that they may interact with each other. So there are many interesting examples. For example, our universe, or we can think about our solar systems can be modeled as an entire particle system. So we have our, with our sun, our Earth, sun, and moon, they will interact with each other through the universal gravities. And also, for example, the flocking of birds in this picture. So the birds, there are lots of flying independently. They usually have some interaction with each other and then form some interesting patterns. And also in social sciences, especially recently, people use the entire particle system IPS to model the opinion dynamics, and also so for the agents in the social network, right? In machine learning, there are also many applications. For example, people use the entire particle system to model or doing some like sampling problems. And also I know some groups they use the IPS to do optimization problem. This is people also usually call this one consensus-based optimization method. So it's kind of like they want the particles to find the minimizer, but instead of just send a bunch of independent particles, so particles may interact with each other and they share information. If one particle or can find the minimizer, can find the sweet point, they will share the information with each other. So this could help us to could help the method, the optimization could speed up the optimization procedures. And also recently, so people also use the IPS to model the dynamics of transformer layers. This is also one of the foundation of our project. So I will revisit this part later. Okay. Yes. Okay, so mathematically, many IPS can be modeled as a bunch of systems of ODEs or SDEs. So of a first order, second order, second order. There are many of them. One of the successful application is the opinion dynamics in the social sciences. So we can think about the opinions of people as a particle. So so here we can think about this xi. So they are the opinions of peoples, maybe a group of peoples, right? And we can think about xi. They take values from maybe from 0 to 10. So if you take a value of 0, basically this means people has a very elective opinion on something. And if you take like 100 or 10, okay, that means people have a very good opinion on it, right? And here, so people may change, the opinions may change. So this is a dynamic system because people usually they chat with each other, right? Okay, so here we use this system, this SDE to model this phenomenon. The peoples or the opinions they may interact with each other through this function phi. So what this phi looks like? Okay, for example, a classic example is that. So we can take the phi looks like here is kind of like the indicator function, but with two values. So if we have 0 to 1 over square 2, then you take a value square 0.1, and if it takes 1 over square root 2 to 1, okay, so the interaction path looks like 1. So how do we interpret, how do we explain why this interaction function looks like that? So basically this means, okay, so because here we have people interact with each other. So typically, we just chat, we just share our opinion with our friends. So our friends usually have very basic, very same idea or same opinions on something. So basically means that if you are friends, then you have the same opinions on something, then the difference of the opinions are small. Okay, so then they will interact with each other. On the other hand, if you have if two people they have very different opinions on something, so this basically means they are not friends. Okay, so in this case, well, they don't interact with each other. They even don't chat with each other, right? So in that case, of course, we cannot they will not modify their opinion according their army, their enemies, right? Okay, so this is why we should the interaction function or the interaction path may look like that. So and then why should we take very small values when the opinion value is small? So this basically means, okay, well, friends they will chat with each other, but right, if we want to, if the group want to attain some consensus, basically means everyone agree on something. Well, it's actually very hard. In that case, okay, the weight will become small. So this reflects the procedure people reach to a consensus. Okay, all right. So I hope this is this is a very, I think this is a very toy is a very toy but very good model for the inert particle systems. Okay, so so now let's say we have this system, this IPS. Okay, so image what happens, how does this dynamic system looks like? Okay, so if there is no noise, that means okay, the system is ODE. So for example, so here we have like 4 people. Okay, they are friends, right? And they basically share the same opinion on something. And then okay, their opinion become to reach to this the same thing. So they become convergence and uh, for example, for these people, so this means this guy maybe have a very different opinions than everyone else. So this opinion is far away from others. So basically means that he or she will not interact with the other. So basically the opinion does not change. Okay, but if we have noise, so the situation become more complicated, right? So the opinions also can be influenced by the noises. Sometimes it's good, sometimes it's bad, right? Okay. So this is the first toy example or first classical examples on the IPS. Okay, and also there are also many. The second example I want to talk about is the Lagrange potential. So this model is very popular in computational chemistry. So this one want to model the phenomenon of crystallized. So we know crystal is not so solid, right? Although the molecules they are formed together and then form a crystal, but the crystal is not so solid. It's not solid as diamond, right? Okay, so why we should have something looks like that? Okay, so people think about can think about this or model this procedure this phenomenon by the IPS looks like basically looks like the opinion dynamics, but with the interaction potential switched replaced by this one. So here the first one reflects a very strong near field repulsion, and the second one is long range attraction. So this this potential tells us, okay, first, if if we have some molecules, they are far away from each other, okay, this potential will attract them together, right? Okay, so they start to crystallize, but there also a repulsion part. So basically, this means when they are near each other, okay, they cannot be close, too close. They cannot be too close. They cannot reach the consensus, okay, because here we have the repulsion. So now let's say what happens. What happens for this model? Okay, still let's take a look at the simulations. So here, these simulations, we basically consider the Lagrange system, but we also put an interaction network between them. So basically, this means well the molecules they have also a network behind them. Not all these molecules or particles will connect with each other. Okay. So for example, here we have the particle 1 connect with 2, but not connect with 3. Okay, and the same here, particle 2 is not connect with 3. So in the first simulations, we can see, okay, we have like six particles. At first, they are kind of far away from each other. Because of the attraction, they start convergence. But when they become closer and closer, very near to each other, okay, then the consensus stopped. Instead, they are kind of doing the mailing, doing the kind of like doing the cycling, right? Because now we have the repulsion dominated. Okay. Okay. In the second simulation, we can basically say the same for a phenomenon. But the one thing I want to point out is that we can observe that for particle 2 and particle 3, well, they are near each other, but they do not attract to each other. So because we have a network behind them, particle 2 and particle 3, they are not connect with each other. Okay, this is why instead of become one crystal, but these two form two groups. Okay. So there are also many other interesting second order IPS. For example, the Osanga models. So here still we have the repulsion and the attraction parts. So this in this model, usually this one used to model the evolution of the phase. Okay, and also for boars. Okay. Another example is about the whiskey model. So this one usually used to model how people walking in a square. So this is a discrete stochastic model. So basically, this means that people, if we have a bunch of people that are walking on the square, well, instead of people don't want to get too close to each other. People want to have some distance between people. So and usually when we walk in the square, okay, so we will change our orientations. So based on the people around us. So this is how they interact with each other. Okay. Well, we already see many examples on the IPS. In this talk, we focus on the max group IPS. That means we only have a finite many particles, maybe 100, maybe 1,000, but still finite. It's not too many. And also, we only consider the first order SDEs. We will basically introduce three systems. The first one is called the homogeneous systems. We have like n particles. They interact with each other through the following systems. They share the same interaction kernel. Okay, this is why this is called the homogeneous. The second one is called the multi-layer attention style dynamic system. So here we have the particles first interact with each other through a metric, and then acting with a potential or a kernel, and then they sum them up doing this mean field. Okay. The last one is the heterogeneous dynamic system. So here we have the particles interact with each other through this kernel phi, but also there is an interaction network behind them. That means some people or some particles they interact with they connect with each other. Some particles they are not. Okay. So this is the three systems or three models we care about. Okay. So for the statistical learning problems, we means that okay. So for example, the opinions dynamic systems we just discussed before, but now we don't know how people how this file looks like. We don't know whether this one is a Lagrange or opinion dynamic system. We just observe the trajectories of particles. We know how those particles looks like. Okay, but we don't know the phi. We don't know the interaction network. Okay, we want to learn them. We want to find them through this data based on their trajectories. So in the first systems, we just want to learn the interaction phi. In the second system, because we have the interaction matrix and also the interaction kernel, so this the interaction rule includes two things. In the last one, we have also the network and also the interaction kernel. But overall, we want to provide some regulars analysis. Okay, for example, the identifiability, convergence, and the minimax rate. Okay. All right. So up here, any questions? All right. So okay. Yeah. Okay. Now let's move on. So this is a typical framework for the statistical learning. So first, we have some data. In our case, we have the trajectories. So this is the training data. Okay. And then we need to have some prior information. So basically means what's the interaction rule should relies on, what's the hypothesis space they should live in. Once we have the data and also this hypothesis space, okay, we can construct the loss function. Okay, so basically we're trying to approximate, so we're trying to estimate the interaction kernel or the interaction matrix. And then, okay, once we have the loss function, we can do optimization and then find the estimator. Okay, once we have the once we finish this step, okay, then we have our estimators. Using these estimators, we can do some prediction. Okay, we can say whether this one is close to the data. Okay, right. So in the next in this part, I will talk about the data learning of the three systems we just discussed before. For the first systems, we talk about the homogeneous entire particle system. This means the particles, they will interact with each other through just one thing, particle interaction kernel phi. So here we can rewrite the interacting parts, basically the right hand side of our OD our SDE, and then we can approximate the speed of these particles, and then we construct the empirical error function. Okay, then basically it looks like that. So once we have the loss function, okay, we can try to find the estimator. Basically means that we want to find the minimizer of this error function over some over a suitable hypothesis space. Okay. Okay. So this is basically what we want to do. If we have some prior information, for example, we know the interaction kernel belongs to some function class, maybe some Holder continuity class, or maybe the fractions of Liouv's class. So in that case, we can rewrite the interaction kernel as the coefficient times the basis. So in that case, once we find the coefficients, then we can have a very good estimator. So if we have phi is just some like finite dimension, belongs to some finite dimension space, then everything is good. We can just we can just solve this least square problem, right? So here we have in this case we can rewrite the error function looks like that. A refers to the random normal metric, and B is the normal vector. So here here the capital B refers to the interaction parts, because we have the particles, they will interact with each other. So here we can see it for this low matrix, they are not independent of each other. Okay. Once we have this least square problem, okay, if we take the gradient, this leads to the estimates. Okay, we have the C hat will be A inverse B. So here A inverse A is actually a pseudo inverse. So why we have why we face this is a pseudo inverse? Because first, this is random, right? Even we have infinite many data, because this is a random metric, there's still some probability A is not invertible. Okay, so and actually in our paper we actually can construct. It's not so hard to construct an example such that A is not invertible. So this is why we always need the pseudo inverse here. Okay, and also more importantly, usually because phi is belongs to some Hilbert space, so it's not finite. Okay. Okay. So this leads to the one of the core concepts in statistical learning, the minimax convergence rate. As we mentioned that we need to find a suitable hypothesis space. So if we know the intelligent kernel, for example, phi belongs to some hypothesis space with the beta degree smoothness. For example, the beta Holder continuity space or the fractional Sobolev space, right? So we can know actually. So in approximation theory, we just need to take the dimension higher and higher, so we can have a better result. However, in statistical learning, this is not the whole story, because we just have infinite many data, right? So if we select a very high dimension of the hypothesis space, okay, although the approximation error become smaller or become better, but we have, because of the finiteness of the data, we have a growing variance. Okay, so in order to find, in order to balance them, so we need to do a trade-off and find a sweet point. So this is at this sweet point. This is usually called the trade-off dimension. Okay, once we find the trade-off dimension, okay, in that case, we can estimate the L2 error between our estimator and our kernel. Typically, if we know this belongs to some H beta, then the rate should look like that. Should be M with the negative power 2 beta divided by 2 beta plus 1 with this decay. So this decay is called the optimal minimax rate. So when I came to Hopkins, so this is the first problem I want to solve, because before us, like our group already have a serious paper on this type of problems. A common strategy is that we can use the Caffey argument and the metric Bernstein inequality, which can prove, well, the minimax rate has a suboptimal minimax convergence rate. So basically means that we can prove the L2 error is smaller than some constant times m with the negative power, looks like that. But in this series paper, they also have suboptimal, because we have another log m here. Okay, so when I came to Hopkins, two lecture questions. First, how to remove this suboptimal factor basically means how to remove this log m. Second, how to match the lower bound. Okay, so well, based on this bias variance trade-off, we know this basically if we follow the same strategy before, we cannot the log m term cannot be avoided. So then our group then introduce a new trade-off. So we call it the bias variance concentration trade-off. Okay. So what does this mean? So first, we notice that because we have random metric, so this guy actually cause a trouble, because it may not be invertible. So first we need to do some truncation and find the event such that the smallest eigenvalue of the normal metric is strictly positive. So here CL is actually a constant, depends on the system. So with this truncation, okay, we can show that the first part is the variance one. Using the Sobolev embedding theory, okay, we can prove this part can be bounded by k divided by m. So here k is the dimension of the hyperspace and m is the number of data. And for the second part, okay, we have the bias, which is decay, looks like a k with the power 2 beta. Okay, the last one is comes from our truncation, and we call it the metric concentration part because this is related to this random metric. Okay, we spent like many pages on this part to how to derive the optimum one on this metric concentration part. So in the end, we found okay, this one is not a big problem because it's decay exponentially. So and with the m divided by and the k power. So in this case, if we select with the choice of the sweet point on the dimension, that means we have the k star. The dimension looks like m with the power 1 over 2 beta plus 1. Then we can prove the R bound is looks like that. Okay. So we can sum it up. So we have, so for beta bigger than 1 over 4, and the H beta is a fraction Sobolev class, then we have the optimum R bound for the first system, the optimum minimax R bound for the first system. So here I want to infer the constant or this restriction on beta. Beta is the smoothness of the fractional Sobolev class. So why we care about beta? Because we know if beta bigger than 1/2, right? So we have from the Sobolev embedding, we know this one can be embedded to the continuous space. So in that case, is rule out the discontinuous functions. But in our opinion dynamics systems, we have the kernel is actually discontinuous. So in some cases, we rarely need beta is smaller than 1/2. Okay. And for the lower bound, we use this fellow Subakov method to do it. So basically, that means it's based on the following Fallow's lemma. Fallow's lemma is about information theory. It's we need to construct a separated hypothesis space, and then such that this separated hypothesis have this KL divergence estimate. If these two holds, then we can have the average probability of testing error is bounded below. Okay. Okay. Well, using this Fallow's lemma, okay, we can so the challenge is how to construct suitable supported hypothesis space. Okay, and then we can bound it below the L2 error. by the maximum over the hypothesis. Okay, and then we can suitably select the separation constant Sm such that the first one is a constant, and also the second part this one based on this Fallon's lemma such that this one is bigger than the testing error, and also the whole thing based on the Fallon's lemma bigger than some constant. So in that case, follow this procedure, we can say the L2 error can be bounded by some constants. But here we have the power m with the 2 beta divided by plus 1. So that means we can match the lower bound, looks like that. Okay, so again, I want to emphasize here for the lower bound, we only show for whole continuity class rather than the fraction Sobolev class. Okay. So as a small summary, so for the first homogeneous systems, we introduce a new minimax rate analysis framework based on our estimator. Okay, we combine the technicals. We combine the metric concentration inequality and also the Sobolev embedding inequality. In the end, we can reach to the optimum optimum minimax R bound. This framework also works for Sobolev space with the beta smaller than 1/2. Okay, and also our framework does not depend on coupling argument, so we can remove this log m. Okay, all right. Okay, then next let's move to the second system, which is the multi-layer attention indirect particle system. So this one the motivation comes from the transformer. We know that the transformer came out by this by the very famous paper "Attention is all you need," and this is a screenshot of the picture on this paper. So well, people believe that the multi-head attention is the K gradient such that the transformer here can performs better than other models. So the for this attention attention model, okay, so we have the input and then we have a QQV matrix, okay, and then we will basically do n time. So in the origin paper, they say we can do 6 times of this encoder. But also people believe maybe we can do maybe we can do more iterations on these encoders and the decoders. So how does this one? How does this transformer relate to the indirect particle system? Well, that is an interesting idea because we can view the self-attention through IPS. Basically, in this paper, in this paper, so people can think about think of the tokens as particles, and also the attentions can have the pairwise interaction with each other. So how does this look? How does this one looks like? So we know for this attention is about the softmax on this QQV matrix, right? So for QQV, we can have them as the X, which is the input, times the WQ, and the same for K and V. So now we can rewrite this softmax in the following way. First, we can combine the WQ and the WK together as a score interaction metric, and then for the softmax, we can write it out in this way. Okay. So now we can so here we have the Z is the is kind of the partition constants based on the softmax. Okay, so now we can say first we have xi and xj. They interact with each other through this matrix A, and then for this partition function, okay, if we have many particles or many tokens, right, then we have the mean field limit. So that means we can reach to a constant z. Okay, so in that case, well, we can if we can forget about the value function of the value metric, let's say take this one as a constant. So in that case, okay, we can rewrite the softmax self attention models as the following way. So this can be think about as one step entire particle systems, but we need to do it. We need to iterate it. So the iterations can be think about the discrete time. So formally, we can rewrite this one as the following multi-layer attention style dynamic systems. So here we have the G star, which is the softmax xi, xj, a, and xi. Okay. Indeed, sometimes we need to introduce the noise to be more realistic. So now in order to well to learn or to inform these systems, well, because this one is kind of it's non-linear system and very complicated. So we tried our previous framework to get the minimax rate, but it seems not so easy. So we go back to this coupling arguments. So using the coupling arguments, we can have the following minimax rates for joint learning, the phi and the a. So in this case, because we are using the coupling arguments, unfortunately we can have the R bound looks like that. So here we have the log m here. So this is we believe this is a suboptimal R bound. But for the lower bound, we find okay, now this is still good. It will be the same as before. So hopefully we can find a good way to remove this log m in the R bound later. Okay. So here I just want to basically introduce talk about a little bit idea on the idea of the proof in the R bound. So now we can decompose the R bound, the mean square error in the following way. So here we have three terms. The first term is still an approximation error, and the second one is a variance part. So and the last one is a truncation part because we need to truncate our our outputs in the following way. So here we have the ym now can be truncated by bm, which looks like log m. Okay, so for the first part, the approximate error, still we can estimate it easily. It will be the dimension with the 2 beta decay. For the second part, now we are using the coupling argument. So the k is to estimate the coupling number, right? So using the following estimates, we can find now this part is bounded by km log m divided by m. So we can say that we can notice that log m is here, and this is why it appears in the R bound. For the truncation error, we're using the sub-Gaussian property, and this can be done this can be done and find the R bound estimates looks like the log m divided by m. Again, if we if we select the choice of the dimension looks like m divided by log m with this power, okay, we can find the R bound. Okay, so in this slides we can say the this dot lines are the theoretical decay, and the solid line is our estimate, our experiment. Okay, one can say that if we change the dimension, and we can change and also we can change the smoothness. Okay, well, we can say that uh, the estimates can actually reflect or coincide with our theoretical prediction. The decay should be the 2 beta divided by 2 beta plus 1. Okay. Okay. So there's some remarks on the second systems on the multi-layer attention models. We extended the technicals in this classic book to analyze the minimax rates for the multi-layer attention type model. The optimum lower bound is obtained, but for the upper bound, well, we have additional log term. So one interesting phenomenon or one interesting condition actually is about this one. So in our proof, we found, okay, so R, which is the rank of A, and D is the embedding dimension, it should be smaller than M divided by log M with this with the power 1 over 2 bar plus 1. Well, actually here, this suggests if we have a rough activation function, basically means that we have smaller beta, right? If beta is bigger, then that means we have this function, the kernel is actually smoother. But with the small value of beta, that means we have rougher activation, right? When beta goes infinity, actually this part, because this one just 0 and this one becomes 1, so we have RD less than 1. So this is not good. So instead, we want this beta actually to be small, right? So this means we can, if we have a rougher activation function, it can tolerate a large dimension. Okay. Okay, so lastly, let me quickly talk about the heterogeneous system. So this is the big picture of our project. So we have particle systems. There are lots only interact with each other with some colors, but also there is an interacting network behind them. Okay, so now we want to estimate both the network and also the kernel. So this part, this is more. I would only talk about the algorithms. We can see that. So we have the uh, uh, based on our algorithms, we can find the arrows on this network is looks like that. And for the colors, we can basically say they are quite good. Okay, so why I think this question or this problem is interesting is that because now we have the phi. Let's talk about the finite dimension case first. So we can identify the interacting parts. Basically, the right part of the SDE looks like that, and we can rewrite it as a low-rank metric sensory problem with the sensory operator B involves with all these all these interacting functions. Okay, so in that case, actually estimate the network and also the kernel is kind of equivalent to the low-rank metric sensory problem. Okay, so in general, we know the low rank metric sensitive problem is non-convex. So actually, we did some experiments. So if we select different bases, for example, Fourier basis or Hermite polynomial basis, and also others, we observed that. So in many cases, well, that's actually we have a local minimum. So that means this is a true non-convex problem with a local minimizer maybe cannot can get tripped. Okay. Uh, uh, in the uh, in the context of low-rank metric sensitive problem, so the restricted isometry property is the most important concept. So the RIP condition means that we for the linear map, we should satisfy the following condition for all these metrics with rank at most R. Okay, so this is very similar to the eigenvalues, but now we only test on the matrix with rank at most R. The RB conditions can provide the conditions for accurate and stable recovery of low ranks. And also it can be also used to show this identifiability and also non-convexity. For example, in this paper, the rank 2R IP condition means that we have the IP constant is smaller than 1. This is equivalent to identifiability. Okay. However, in our problem, because we consider the hypothesis space may have the infinite many dimensions, so we need a functional version of IP. So in our paper, we define the following three types cohesivity condition which closely related to the IP condition. The first one is called the rank 1 joint cohesivity condition. This is a functional version of the rank 1 IP, and the rank 2 joint cohesivity is the rank 2 IP condition. And the last one is related to the full rank IP condition. So well, I don't want to talk about the details, but from the names, we can say the last one is strongest, and it implies the rank 2 and the rank 1. So in our project, we introduced two algorithms to find the network and also the kernel. The first one is called we call it the optimization the honors, which is based on automate regression and the alternative square. So in this algorithm, we first using the operator regression to find the z, and then we use the alternating least square to recover the network and also the kernel. Okay. So for this algorithm, we can have the we can prove the convergence of the algorithm, and also we show that the estimate has the asymptotic normality. Okay. And also we have another naive alternative square algorithm because we can in this case we can think about first we freezing let's say we freezing this color. Okay, now the problem the arrow function is actually convex on the network. So in that case, okay, we can find A, and then we freezing the network and to find C. So this naive alternative square, of course, we cannot. It's not guaranteed that finally it can reach to the global minimizer, because we know we have the local minimizer for most of the problems, right? So in this case, the convergence is not guaranteed. At least the theoretical is not guaranteed, but empirically, Okay, we tested it, and in most of the tests, well, the ALS, the naive or the least square rarely gets achieved by the log minima. So this actually surprised us. Also, so here we also have a theoretical results summary of our paper. Basically, the K is about all these cohesivity conditions, and also how these conditions can guarantee the performance of our algorithms. Okay, so so here is the numerical results of our algorithms. So we can see that as the data, the number of data become larger, while the estimate errors become small. For the for the orange one, this is the color error, and the red one is the trajectory error, and also this green one is the graph error. We can observe that for two algorithms, the dash one is about the Aulus, and the solid one is ALS. So Aulus need more samples to guarantee the convergence, and the LS need a much smaller sample in some cases, and it starts decay. And also, we also test about the length of the trajectories. How does this one can help us? Okay. Okay, so maybe in last 5 minutes, I will talk about some applications. The first one looks like that. So we can consider a leader-follow system. So this basically means that in a systems, we have different types of peoples or different type of particles. They interact with each other through this network. So typically, we know that we can think about that. So we can assume that if someone can influence more people, well, or it connects with more people, this particle should be a leader, right? In that case, okay, we're trying to learn this network. Okay, so for example, here we have A1 and A6. They are the leaders of the red and also blue groups. Okay. So I don't need to emphasize that if we have small data, for example, we have just 50 trajectories. Well, in that case, typically we cannot find the correct, so the accurate network, right? So this one is the estimated network, and the right one is the ground truth. We can observe they are kind of far away from each other. Okay, and if we have more data, okay, the results become better and better. So if we have 100 data, okay, we can accurately estimate the network. But the thing is that although in the first two scenarios we have okay, we don't have enough data, but still in that case we can cluster the groups correctly, right? So for example, if you just have 50 data, okay, we can still identify A6 is the leader, A1 is the follow, A1 is the leader of the red group, and also the follows are also correctly clustered. Okay. So this means that because in this system we have dominated features. So even though we cannot estimate the features correctly, but still because this is dominated, so still we can correctly cluster them. And another application is about actually this is a new project. Actually, we consider two types of interaction colors. So, for example, in the predator system, so we don't only have one type of particles, but have many types. We have prey and predators. So in this case, if we just load the trajectories, how could we recover the how prey and prey interact and how prey predator interact? Okay, so this is the problem. Okay, so well, I don't want to talk about too many details on that, but based on our algorithms, still this can be estimated correctly. Okay. Well, okay. Think this is the end of my talk. Thanks for your attention.
Yeah, thank you very much. Any questions or thoughts or comments?